Hey everyone, today we'll be starting our first steps towards the deep learning course. First, I have decided to recap of the linear algebra concepts, some of the basics stuff, just to build upon while we go. And you can also take it as a appendix for the course. So let's get started. Some keywords first needed to be established in our minds to understand how the linear algebra is cosmos is basically working with each others. First thing is the space. So the space actually is the place where the vector lives. So each vector is being any transformation being applied on such a vector will be applied within such a space. So if we stretch, if we squish, if we transform any kind of transformation, it will exist in the same space of this vector. We have four spaces. Basically, there are two main and two others suspended from such main spaces, like the column space and the null space. And the branches from this are the column of A transpose, which is the row space, and the null of A transpose. The column space actually of the matrix A is all the linear combination of the columns of the matrix, and the row space is all the linear combination of the rows of the matrix. You will understand what I mean in the next point. So basically, this is an image of the space where the vectors lives, and this is the linear combination of basically just two vectors inside this space. And these two vectors are called the main vectors, or more exactly, the basis of the space. So what does the basis mean? If we can understand it in a way just to make it simpler, if we have the colors and we can consider it as the vectors. So each color is a vector. And this vector is composed of three main components, the red, green, and blue. And it's just every proportion of the red and green and blue will generate a new vector. So these three vectors, red, green, blue, are called the basis of the color space. So these vectors can construct as many vectors as you can. Like they can be infinite number of vectors as you take a certain or a specific amount of each color and mix them together and then generate a new color. So this process is called the linear combination. We just take a certain amount of each color and mix them together. So this mixing can be transformed in the linear algebra lingo as addition, and take amount is multiplication. So I just multiply this vector by a certain amount. I take a certain amount of this vector and mix it with each other. So this will generate a new color in the color space. And if we take infinitely many combinations as we can, like if we take from this C1 and C2, C3, from negative infinity to infinity, and fixing one and changing the others, fixing one and changing the other. So this will generate too many vectors. These vectors will, this is the span of these vectors, okay? So this span will fill the space. For example, in this picture here, we have just 2D plan. So this 2D plan is basically constructed from two main vectors, which are the basis. You can see the x-axis and the y-axis can be the basis of this space, but not necessarily these are the only basis. because actually the bases have not don't be to be unique, don't have to be unique. Like they can be, we can take any other two vectors here, and also they don't have to be orthogonal. It's good to be orthogonal, but they don't have to be orthogonal. Like they cannot be. They can be two simple vectors with any angle between them. So this, the main 2 points is the first 2 points. Like they should be linearly independent. Like they cannot be created from other ones, and their span should fill the space. Okay, so if we have a matrix and this matrix contains 3 vectors, so these 3 vectors, I should not be able to pick one and try to describe it within the other two. In that case, this vector cannot be independent. It is dependent on these other two whom described this vector. So also, if we need to check whether these 3 vectors are linearly independent or these are the bases, I can put them inside a matrix and apply a function which called the determinant. If the determinant is 0, then one of these vectors is dependent on the others, or more. Like it cannot be. But if it is not 0, they need to be, these vectors are all linearly independent. They are all the basis of this space. Okay. Another thing is the span, which been described earlier. Like it is the all linear combinations of the bases or the linearly independent vectors. And if we take an example of a single vector, so this single vector can have a single magnitude. I take a single amount, and I take as infinitely as many as possible number of scalars. I can multiply it by from negative infinity to infinity. So it is a huge number, and it will create a huge number of vectors, but all these vectors will be aligned on a single line. So this vector, or the linear combination, all the linear combination of this vector will be generating an infinitely long line. Okay. The same thing if you have 2 vectors which are linearly independent. So this, if I take all the infinite linear combinations, I can generate a plan. Okay. An infinitely huge plan. And if there are 3, I can generate an infinitely huge sphere. Okay, because this is the span, and it fills the space. Okay. Okay, so for example here, if I take these 2 linearly independent vectors, like I cannot generate this v2 from v1, I cannot generate from 4, I cannot get 5, and the 3 to get 2, so there is no single transformation to generate this vector given this vector. That's what linearly independent means. They cannot be created from each other. So these 2 vectors can span a 2D plan. However, they are in a 3D dimension, but they can span 2D plan. Okay, so they can be the basis of this space. And if I take a new vector, which is a linear combination from these 1, I take 2 from the first vector and 3 from the second one, so it generates a new vector. But this new vector will exist in the same base of these 2 vectors, will be existing in the span of these 2 vectors. Okay, so the Q1 exists within the span of V1 and V2, and it is dependent on them. Fine. So let's interpret it in another way, or make it, instead of just addition here and multiplication, we can make it in a matrix vector transformation. Like I can pick these vectors and insert them into a matrix, 2 columns here, and get these 2 magnitudes inside a column vector. okay, and start to multiply these by these to generate this number. So here matrix vector multiplication can be described in two ways. The first thing is the column combination, and the second part is the row combination. So these interpretations have different meanings and can be useful in some parts to understand some other spaces, as we have mentioned, like this is a null space. But here, for example, we are all in the column space of this matrix A. So, like, if I take this combination, any combination from these columns will generate a new vector. This vector is existing within the column space of this matrix. Fine. Okay. So just to take a note of this multiplication here is the same as taking 2 from the first and 3 from the second. And try to also understand the dimensions, because dimension should be aligned. This is 3 by 2 and it's 2 by 1. So the output should be 3 by 1. Okay. For example, here I have 3 vectors. So if I told you I have 3 independent vectors, so how can they generate? What is the output of this span? So yeah, it should be a sphere. So this sphere is the span of these 3 vectors, all the linear combinations from these vectors. And such a span will be the column space of the matrix A, which will be all the combination of AX, where X is any constant can be added, can be multiplied by this matrix A. And this X can be a vector, and AX will be transforming this vector into another vector, and this another vector will be existing inside the column space of the matrix A, will be existing in this sphere. Okay. So where AX or where B exists, it exists within the column space of this matrix. It is in this sphere. Okay. And another question, which is somehow different one, which could be doesn't exist within this column space. Like, can we generate a vector out of this space? That's the question here. So the answer is yes, which we call the null space. And the null space is a different space. We will describe where exactly it is relatively to the column space, but it's different from the column space. And this null space actually exists if and only if there exists dependency in the matrix. As I've told you, if this matrix contains all linear independent vectors, then there exists no null space. Only the column space exists. But if there exists, for this example, like this 1 plus 1 equals 2, and 1 plus 2 equals 3, and 1 plus 2 equals 3. So this third column here is actually depending on these two. Okay, so in that case, we can say this matrix is not linearly independent, or all the vectors of this matrix are not linearly independent. So this column is existing in the null space. Okay, because there exists a dependency between these vectors. So for example, here I say this v2 is just the addition of these two vectors. So if I move this magnitude here and outputting this will be the third vector on this matrix, which will be the addition from these two vectors, and it exists in the span of these two vectors or in the column space of these two vectors. But this, if it exists in this matrix, then it actually not adding a third dimension. If I look into this matrix, it is the 3 by 3. So it should span a sphere. But as you can see here, the third vector exists within the same 2D plan. So in that case, it doesn't add any new information to the matrix, to the data. So our data now is dependent, so I can remove it. And the matrix, I can just only take the first two vectors as on my data. And this third vector, I can neglect it because it can be generated. Okay, so basically this is, there exists here a null space. Okay, because this dependency relation. So the question is, how can I find this null space? Simply, if we set ax equal to 0, where x not equal to 0, because it will be naive solution, any x that satisfies this equation, this x is, can we say, the basis of the null space, because each space have a basis. So this x will be inside the null space because it satisfies this equation. Apart from it is not equal to 0 because anything multiplied by 0 is 0. So this x shouldn't be 0, but should be a vector. From this example, I can see, like, simply we can make it -1, -1 by 1. So I can multiply this first column by -1, -1, and this last one by 1, and start to add them. They will be outputting 0. So this vector exists in the null space, and it's the basis of the null space. And also any magnitudes or any constant being multiplied by this vector or any linear combination will generate a span, and this span is a line because it's a single vector. So this line is the null space. So the column space of this matrix is a plan, a 2D plan. It's not a 3D. It's not a 3-dimensional, it's just 2-dimensional. And the null space here is a line. Okay, hope it's clear. And this x exists within the column space, within the null space. Okay, so here, where does the null space exist relatively to the column space? Actually, if you remember from the linear algebra part, there exists something called the dot product that we'll be discussing in a few minutes. But first, here is the matrix vector multiplication. As we can say, it can be interpreted in two ways. The column space, like I take the first element of this, because here should be 3 elements because I have 3 vectors. So each element should be multiplied by each vector, generating a new vector, which exists in the column space of this matrix. Okay, so this x here can be divided into 3 items, x1, x2, and x3. And these 3 x's can be multiplied by these 3 vectors. So this is the interpretation in the column, combination of columns. Okay, so this is a first interpretation. The second interpretation is the row. If we have written it in the row way, so this vector, this row, will be multiplied by this column. Okay, all these vector will be multiplied by all these column, and this is the row interpretation or the combination of rows. So if you remember from the dot product part, what is the dot product? It is basically multiplying a row by a column and generating a single number, because here this row dimension is 1 by 3 and this x is 3 by 1. So the output will be 1 by 1. So it's a single value and it's a scalar. And since we are here talking about the null space and about this equation, any solution satisfies this equation, so it exists in the null space. So if we inserted this -1, and 1 inside these x's and these rows here inside this q1, q2, q3, so the output should be 0. For each of these parts will be 3 zeros due to these 3 dot products. And if you remember from the dot product properties, if the dot product of result is 0, then these two vectors are orthogonal, perpendicular to each other. Hence, if we have these vectors are perpendicular and these vectors are the rows of this matrix, and this vector, the other vector is the null space basis. So basically, this is the row space and this is the null space. And since the relation between them is perpendicular, so the row space and the row space and the null space are orthogonal to each other. Okay, so this is where the null space exists. It is orthogonal on the row space of the matrix. Okay, so now let's get back to the somehow the deep learning or machine learning part and start describing what is the regression or what is the linear classification basically is composed of. So if we have W by X, W actually is the weights of our model and X is the input, the data. So basically if we have this input and our matrix W is composed of 3 vectors. These 3 vectors can be 3 different directions that can be describing the weights. Okay, so any vector being multiplied by this matrix W, it will be moving the magnitudes of this vector in these directions. So this weight matrix is transforming this input vector into another vector. And this other vector, which we are calling the prediction of the model. So the model actually is transforming the input into another space. And this space or into another vector. And this vector exists within the column space of the weights of our model. So here, for example, if we take 2 in this direction, 2 steps in this direction, and 3 steps in this direction, and a single step in that direction, so the output will be a single vector. This single vector is the prediction, is a y hat, and this y hat is existing inside the column space of our W. So what are we doing when we are training our model? We actually are trying to minimize the error, okay? And in order to minimize this error, we need to change this weight. And since this weight matrix is randomly generated, any machine learning part, we will be generating these weights random way. It can be in a certain conditional way, but by default, it is randomly generated. So by default, it is linearly independent. Okay. So hence, this linear independence will be our target here is to train our model. So in that case, we are changing or modifying these vectors. We are modifying these 3 vectors. These are the basis of the weights. So in the training theme, we are modifying the basis. We are changing the basis of the matrix in order to optimize the transformation and to minimize the error being generated. Okay, hope it's clear. Okay, so this is a linear transformation of X with respect to the column space of the weights, the W. And the objective here is to find the best transformation, the best weights, which will be transforming our input X in order to minimize the error. So we are training, we are changing the basis of the weights. We are keep changing the basis until you find the best weight matrix, the best transforming matrix to the X. In another way, you can see here, this number of points here are scattered, and after being transformed by the weight matrix, they can be in such a way. So it is not necessarily to be a single weight matrix. It can be multiple weight matrices and being multiplied like a hidden layers in the deep learning lingo. We can say like this hidden layer is transforming the input into a different space from the input space, because the input data is existing in a certain space, and after the hidden layer, after a single hidden layer, it changes, the space is changing. So after multiple hidden layers, we are trying as far as possible to make it easily separable for the last output layer to predict whether it is, for example, a cat or a dog, a 0 or 1. So this is the hidden layer's objective, is to make it easy for the output layer to classify the input. Okay, to make these classes easily separable. Another thing is the neural network. And here, as we can see, this hidden layer, we have a single hidden layer here, which will be of 30 neurons, and the input layer is 784 neuron. So this input layer is basically all the pixels of this image. Okay, so this image is being flattened, like this 2D dimension is being flattened into a single vector, where this vector is this 784 neuron, and being applied, inserted into this neural network, which will be having this first weight matrix, which will be of dimension 30 by 784. It's a little bit large. And after this hidden layer, there will be the output layer, which should be taking the inputs from all these neurons and trying to predict, estimate what is this image class, whether it is 0, 1, 2, 3, or 7. So here, as you can see, it is being predicting the 7 as the output of the model. Okay, so this is the main idea of the hidden layers, like they are transforming the input image into a different space to be easily separable or easily being predictable from the output layer. Okay, and of course this transformation is not linear. Okay, so this will be applied by the activation function, which we'll be discussing in the deep learning course itself after this. Another thing is the convolutional neural network, which is a more improving version of classifying images. Like if I have a single image of this will be transforming, a small image can be transformed into 784 neurons. So this will be a pretty much huge number. And if I have an image of 1000 pixel by 1000 pixel width and height, this will be a million of neurons. So in that case, the authors of this convolution neural network have decided to make an improved or less computational power network, which will be learning the images in a more efficient way without using much resources. Okay, because here the number of parameters is huge. Like if you can imagine, it's a single layer. If I have normal neural network can be having 10 layers, or maybe now this huge number of, if you can see the GPT or the Parrot or the ChatGPT is a huge number, billions of parameters. So in that case, we'll try to optimize as far as possible our learning, or minimize the number of parameters as much as possible without affecting the performance of the model. Okay, so here the convolution neural network is transforming also the image into a new space in a different manner than the neural network, the dense neural network, as it will be detecting some simple shapes from the image and making these parameters trying to detect the most beneficial or most influential features from this image, and concatenate all these filters output, because this is the output of the filters. So we'll be concatenating them and inserting them into a neural network, which will be much less number of parameters needed to learn this. For example, here, if you can see, this is detecting the horizontal, like the horizontal edges, and this is detecting the vertical edges. So every filter is having a simple task to detect, or a simple detect curves, detect edges, and by moving forward through the neural network, it will be detecting a more helpful shapes like detecting the eyes, detecting the nose, detecting the ears. And in that case, it will be an influential feature for the neural network to detect upon, to classify, to depend also upon. Okay, back to linear algebra. Like here is the rank of the matrix. Simply, the rank is the maximum number of linearly independent columns. So if, for example, I have a matrix of m by n, I have m rows and n columns. For example, I have only 5 rows and 10 columns. If this matrix have these 10 columns as linearly independent, so this matrix is a full rank matrix, because the rank of the matrix is the 10, not the 5, is the maximum of these 2 dimensions. Okay, so a full rank matrix if the rank of the matrix is equal to the maximum of the 2 dimensions of this matrix. And we also can use this into checking the linear independence of the matrix. Like, how can I say this matrix is linearly independent? If I check the determinant of this matrix is not equal to 0, and also I have this Gramian matrix, which is X transpose by X. We will be seeing it maybe in the PCA lecture, the principal component analysis. And this matrix here, if I take the determinant of this matrix, then this matrix is a full rank matrix. Okay. If it is not equal to 0, if the determinant of this matrix is not equal to 0, then this matrix is a full rank matrix. Okay. Last part here is the singular and the non-singular property of the matrix. Here I have described it in a simple table. I can discuss it in a way like a singular matrix is basically a single direction. It cannot be, it can just go forward. It cannot be getting backward. It can be transformed in a single way, but the original shape of this matrix cannot be recovered of this transformation. Like this transformation, for example, it squishes the matrix. Okay, so I cannot recover from this squishiness what is the original shape of this matrix. So in that case, it is a singular. It is a single dimensional way. So it is not invertible. I cannot get back to the original shape of the matrix, and it has no inverse. So it is just a single way, and it has infinite solution. I can get from this squishiness into as many possible as I can shapes. Okay. So this is where the null space exists. And if the null space exists, then of course the determinant is 0. So just these points being aligned together to remember what is the singular matrix. And the non-singular part is the opposite of it. Like it can be recovered. This transformation, for example, this rotation can be recovered back to the original way, and it can have an inverse because this is the inverse of this transformation. And also it has a unique solution, like this is the only one transformation which get back to the matrix. I have an A inverse, and of course this matrix doesn't have a null space, and it is invertible and have a unique solution. And if it doesn't have a null space, then of course the determinant doesn't equal to 0. Also here, like 2 more features from the non-singular matrix, which we all like, which is a good matrix. Like the Gauss reduction yields also always to identity matrix, and any map that A represent is an isomorphism. This doesn't need to be discussed because it will be a little bit more advanced, but only these 4 points here are the most important parts to distinguish between a singular and a non-singular matrices. Hope this lecture is clear and see you next time. Goodbye.